in this video, we're going to look at some examples for chapters 3 and 4 for Chem 121. So we're going to look at an annotated periodic table that is in the shared folder. We're going to look at some electron configuration, some orbital diagrams, some ions, and then we're going to look at some polyatomic ions. So let's look at an annotated periodic table really quick. So in the shared folder, there is going to be this annotated periodic table, which I've included the periods, the rows, or the groups, and then I've included the S, the D, the P, and the F down here. And so when you're doing the electron configuration, you'd go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, excuse me. And so that's going to be kind of the form that you would going through trying to do the electron configuration. And then I include the ion numbers, so cations being positive, anions being negative. And you can see down here that I've included a +1, +2, +3, ±4, -3, -2, -1, 0. And those are going to be the ions for each of those columns. And then I've included, you can see that we have this bar, and that'll be your metalloids, or this baby blue color. And then I've included the diatomic molecules that you might want to memorize because sometimes they might be helpful to reference or remember what those are. We look at some polyatomic ions that are common that I think will be helpful when you're trying to name a compound or something like that. I include some prefixes as well, and then I include the density triangle and the moles conversion triangle, so going from liters, grams, and particles. So let's look at some electron configurations for this. Our first one. So we have nitrogen, which is going to be the atomic number 7. If we go back and look at our periodic table, and we want nitrogen, we're going to go 1s2, 2s2, 2p3 would be 1s2, 2s2, 2p3. And you can remember off the top that if we're looking at the 7, and if they're neutral, we're going to have 7 electrons and protons. However, this would be our answer. And you can look back at, if you look at the exponents, so a 2, and a 3, and if you add those together, you should get the amount of electrons and protons that you have. So let's look at the next one. So now we have aluminum, and we know that we're going to have 13 electrons and protons. And if we go back and look at our periodic table for aluminum, we go 1s2, 2s2, 2p6, 3s2, 3p1. And so our electron configuration is 1s2, 2s2, 2p6, 3s2, and 3p1. And if we add those exponents together, so 2, 2, 6, 2, 1, will equal the 13 protons and electrons that we have. So now we have argon, and we want to get the electron configuration for argon. And we know that if they're neutral, we're going to have 18 protons and electrons. And for argon, if we go look at our periodic table, we go 1s2, 2s2, 2p6, 3s2, 3p6. So our electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6. And if we add our exponents together, 2, 2, 6, 2, 6, it will equal 18. So let's look at copper. And copper is one of our transition metals. And for now, we're going to say that there's 29 electrons and protons. And if we go back to our periodic table and we look at this, we have this D less than 1. So when you go through the periodic table and when you get to the transition metals, you're going to take that front number and you're going to bring it down 1. So for example, we want to get to copper down here, 29. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9 would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. And if we add those exponents together, we will get 2 plus 6 plus 2 plus 6 plus 2 plus 9, and it will equal 29 that we found for the atomic number. So I know there was a point where you might have heard of valence electrons, and those will be whenever you get to this point. So if we looked at copper and we wanted to know the valence electrons for these, we want to look at the highest energy that we have. So in this case, it would be the 4s or the 3d. And so we would take the valence electrons off that one, or ions off those ones. So we looked at this one. So for 26, we have, for atomic number 26, we have Fe, and that will be iron. And we want to find what our electron configuration for this would be. So we have Fe to the 2 plus power. And so for now, we want to write the electron configuration for Fe26, but we're going to lose 2 electrons. So we're going to do the electron configuration for iron, so the full 26, add our exponents together, make sure it's right, and then we're going to take 2 electrons from it. And so we'll pick the highest power in that case. So if we go to our periodic table, we go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So for 26, we get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. And if we add those exponents together, we'll get 26. However, since we're losing 2 electrons, we're going to pull it from this one right here. And so our electron, we would go down to 24, but we would keep this slot. And so our electron configuration would be for Fe 2 plus. Our electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, 3d6. So let's look at chlorine, number 17. And we want to find Cl1 minus 1. And we are going to look for, we're adding an electron. So we're going to want to look for, we want 18, our exponents to add to 18 electrons. We look at our periodic table once again, and we want 18. So we're going to do the electron configuration for argon in this case. So our answer would be 1s2, 2s2, 2p6, 3s2, 3p. And if you add those exponents together, you will get the 18 that you're looking for and that you need. So next, we're going to look at orbital diagrams. And if you have the electron configuration, you can... So if we wanted to go all the way up to 4s, and we know that the s's is going to only have 2 electrons, the p's are going to have 6, the d's are going to have 10, and the f's are going to have 14. And so each space is only allowed 2 spins or 2 electrons. So we write them as spins as arrows. So if we want to go all the way up to 4s, there's a pattern that you go. So you're going to go up arrow, all the way up that whole thing, and then go back to the down arrow. So for example, if we went all the way up to 4s, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And so you fill the row first with up arrows and then go back to fill them with down arrows while you're counting up to that number of electrons for that given element. So this is kind of the hierarchy or I would say hierarchy or the way that they're leveled, which is just an image. And so you can see you go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, and so that's where you're going to hit the transition metals. And then you're going to go back to the other side with 4p6, 5s2, and so on. So let's look at some examples. So let's say we have nitrogen, and we know we have the electron configuration for nitrogen as 1s2, 2s2, and 2p3. And if we add those exponents together, we're going to get the 7 for the atomic number, because we know that atomic number is going to be equal to the number of protons or electrons in that given element, as long as they're neutral, or as long as they're not gaining or losing any. So if we look at doing the electron configuration for this, we want to go up to 7. So we're going to go 1, 2, 3, 4, 5, 6, 7. And so this right here would be your answer for that given element. So let's look at magnesium. So we know the electron configuration for magnesium is 1s2, 2s2, 2p6, 3s2. And so we can similarly do the same thing we did with this one on the next one, on this one. So we want to go up to 12. So 1s2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so our orbital diagram for magnesium. So let's look at aluminum, so 13. So we know that our electron configuration for aluminum would be 1s2, 2s2, 2p6, 3s2, 3p1. So if we go up to 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And on the next one, we're actually losing 3 aluminums, or losing 3 ions. So we want to write the electron configuration for that one. And if we're losing, we're only going to do 10. We're only going to have 10 available. So we would take it from these two, since they're our highest energy, so 3p and 4s. So since they're our highest, we would pull it from those. So we would lose 3. So 13 minus 3, it gives us 10 electrons. So if we go up to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then that would be your aluminum 3 plus configure orbital diagram. So let's look at sulfur, and we know that the atomic number for sulfur is 16, and yet we're going to be gaining 2 electrons, and so we want the electron configuration for 18 electrons. So for 18, we know that the electron configuration is 1s2, 2s2, 2p6, 3s2, and 3p6. And for 16, we would have 1s2, 2s2, 2p6, 3s2, and 3p4. And since we're gaining 2 more electrons, we're going to go up to 18, and so we would use this electron configuration right here, up top. So if we wanted an orbital diagram, we could go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And that would be your orbital diagram for sulfur -2, 2 minus. So let's look at this transition metal, and we're going to be losing 2, and we know the electron configuration for this one is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. And so if we look at our periodic table and we start at our noble gas above the row that it is, and so we're looking at 27. And so if we look at our noble gas above it, so if we look at argon and we start from argon, it would be 4s2, 3d7. So you could write it. So if you start at argon, you got 4s2, 3d7. And since we want to lose 2 electrons, we're going to pick it from the highest. So our highest would technically be this one with the 4 out front. And so our new one, our new electron configuration for 2 plus would be 4s0, 3d7. So if we wrote out our orbital diagram and we followed our electron configuration, we would leave 4s as 0 and then go up to 3d. So let's look at some ions. And so we have this valence electrons, and so we go from the left column, 1, 2, skip the transition metals, 4, 5, 6, 7, and 8. And so those will be your valence electrons for each of those columns. Then we know that a full octet is the atom that wants to be 0 or 8 in the outer shell. And so we know that we have this key on the bottom that's going to be L is lose, G is gain. And so for the first column, we're +1, +2, -3, plus or minus 4, -3, -2, -1, and then we have our zeros for our noble gases. We have Roman numerals in case when we're naming our compounds, and we can use those to specify how many of ions or electrons that this given element has. So when we're naming them, we'll use them. And then some common polyatomic ions that might be help when you're trying to name. So let's look at our first one. So for our first one, we have sodium chloride. And if we look at our periodic table, for our Na, we're going to be on the +1. And for chloride, we're going to be on the -1. So if we wanted to write the chemical formula for this one, we would have Na +1, or 1 plus, Cl 1 minus. And since the ratios are 1 to 1, we don't have to cross, and so our chemical formula would be NaCl. So let's look at calcium sulfide. And for calcium, if we look at the periodic table, we're going to have calcium as a 2A, 2 plus, and our sulfide would be S -2. And since they're the same ratio and the same ion, we don't have to do any crossing, so our chemical formula would be S, or CAS. So next we have gallium bromide, and we know that gallium is going to be Ga 3 plus, if we look at our periodic table. And then for bromide or bromium, we're going to have Br minus 1. And so if we cross our charges, we get GaBr3. So next we have magnesium phosphide. And so if we look at our periodic table, we know that magnesium is going to be Mg2+, and phosphorus would be P3-. If we cross our charges, we would get Mg3P2, and that would be our chemical formula. So next we have potassium sulfate, and if you remember from the polyatomic ions, sulfate is going to be SO4 2-. So for potassium, we're going to have a K, and then we're going to go 1+, and then we're going to have our sulfate, so SO4 2-. Since the charges are not 1-to-1, we are going to cross our charges, and our chemical formula would become K2SO4. So next we have strontium phosphate. And phosphate, if you look back at your polyatomic ions, will be PO4 3-. And for strontium, we have Sr2+. If we cross our charges, since they're not 1-to-1, we get Sr3PO4 2. And that would be your answer. So next we have the Roman numerals, and we have iron 3 sulfide. And so it tells us right here that we have 3 iron, and we have sulfide, and we know sulfur is going to be 2-. And since we're not 1-to-1, if we cross our charges, we get Fe2S3, and that would be your answer. So let's look at naming some of these formulas. And so if we have NaCl, if you look at our periodic table, we're going to have sodium, and naming convention for the metals is going to be taking off the ending and adding IDE. So your answer would be sodium chloride. So for the next one, we have MgBr2. And so our naming compound would be magnesium bromide. The next one, we have AlF3. And so we know that Al is aluminum. And 3 would be fluorine fluoride. The next one, we have CaO, and our name would be calcium oxide. So next, we have some of them that are going to be polyatomic ions, and we're going to name them as the polyatomic ions that they're shown. So for this one, we have lithium. So we'll have lithium sulfate. For the next one, we'll have sodium carbonate. And for the last one, if we look at it, it will be barium hydroxide.